Okay, so action. Then it checks whether the jth process also wants to enter the critical section or not. Okay. So if jth process wants to enter the critical section, then the jth process will set flag j to true, and ith process will wait in this while loop. But still, this solution is not problem free, because the same logic which we applied in our previous case, if we apply in this, say first ith process sets flag I equal to true, then before ith process enters this while loop, the jth process also sets flag j to true. Then the jth process enters the while loop. So ith process now will find that flag j is true. Jth process similarly will also find that flag I is true. Okay. So both the processes, the ith process and the jth process, will remain in this while loop indefinitely. Okay. So our requirement of progress that the decision of who will enter the critical section must be taken in finite time. So that is broken here, because both the processes will enter in this while loop, waiting for the other process to reset its flag. Okay. So naturally, this also cannot be a solution to the critical section problem. Okay. So I just told all these things to indicate that what are the problems that you can face and how to analyze whether you are meeting the requirement or not. Okay. Now with this background, let me give you the correct solution for two processes. The correct solution will be something like this. Again, as before, we will assume that there are some shared variables. So in this case, when the shared variables will be one is flag, so we'll have flag as before, that is an array of two elements of Boolean, and in addition this will also use the shared variable turn, which can assume either value 1 or value 0. Okay. And initially all the elements of flag are reset to false. Okay. Turn can have any value, either 0 or 1. Then we can write the program like this. For the ith process, pi, it will set flag I to true, then set turn to j, so this is the entry section of the ith process, and this is the exit section of the ith process. Okay. Now let us try to analyze to see whether this gives the correct solution or not. Now the approach that is taken in this case is, firstly, the ith process indicates that it wants to enter the critical section by setting flag I equal to true. Then the ith process sets turn equal to j. It is an assertion. Though ith process wants to enter the critical section, but it just tries to check whether jth process also wants to enter the critical section or not. So ith process has registered its request by setting flag I to true. Then it asserts that let it be the jth process's turn to enter the critical section. So it sets turn equal to j. Okay. Then in this while loop, it checks whether flag I equal to true or not, flag j equal to true or not. So if the ith process finds that flag j is equal to true, that means flag j will be set to true by the jth process in the intersection. So if flag j equal to true, that indicates that jth process wants to enter the critical section. Okay. Then ith process has set turn to j, asserting that let it be the jth process who will enter the critical section. So if both of these conditions are true, that flag j is true and turn is also equal to j, then ith process will remain in the while loop. Okay. If any of them is false, either turn equal to j, this can be false, or flag j can be false. Flag j can be false in case when the jth process does not want to enter the critical section. Okay. So if any of them is false or both of them are false, then the ith process will enter the critical section. Now, how this while loop is broken? We have said that turn is a shared variable which can take value either 0 or 1. Okay. And this being a single variable, it can assume only one value at a time, depending upon which process, whether ith process or jth process, executes this turn equal to j or turn equal to I first, last, that value will be returned. And accordingly, either ith process will enter the critical section or jth process will enter the critical section. So even in situation when both the ith process and the jth process wants to enter the critical section simultaneously, first what they will do, both of them will set their corresponding flag to true. Then ith process will set turn equal to j, jth process will set turn equal to I. Now, whichever this assignment statement is executed last, turn will retain the same value, that particular value. Okay. Accordingly, for one of the processes, either this while loop, either for ith process or for jth process, this while loop will be broken. Okay. And that process will enter the critical section. When the process comes out of the critical section, it sets the corresponding flag equal to false. Okay. Because it sets its flag equal to false, so if it is the ith process who has entered the critical section, the ith process in the exit section sets flag I equal to false. So for the jth process, which is now waiting in the while loop, the jth process will find that flag I is false. So while loop will be broken and jth process will now enter the critical section. Okay. So you find that if you follow this, you will see that this meets all the three requirements, that is mutual exclusion, progress, and boundedness of the critical section problem. Okay. So naturally, this is a correct solution for a two-process critical section problem. Okay. So you have seen that how we can write a correct solution to a critical section problem involving two processes. Okay. But in general, in a system, there can be n number of processes. So we have to see that how the critical section problem can be solved for n number of processes. Okay. So I'll just give you the algorithm without analysis. You try to analyze this algorithm. For n processes, our algorithm will be slightly different, and obviously it will be more complicated than what we have done for two processes. So here, for n process, again we'll have a number of shared variables or common variables. The common variables in this case are, as before, we have an array flag. This is an array, but in earlier case, the array had only two elements. In this case, the array has to have n number of elements. So it will be indexed from 0 to n minus 1 of, in the previous case we had assumed that any element can assume only two values, either true or false, but in this case we will assume that an array element can assume one of three values. The three values we put as idle, wanting, or in CS. So these are the three values that any element of the array flag can assume. Okay, and we also have a shared variable turn, which is an integer variable, and that can assume a value from 0 to n minus 1. Okay. Then for the ith process, Pi, the solution will be something like this. Yeah. The ith process itself will have a local variable, say j, which can assume values from 0 to n. Okay. Then empty section will be like this. Okay, so this forms the entry section okay, and after this entry section you have the critical section, and in exit section the code will be something like this. So after entry section we have critical section, then in the exit section the code is like this. So this is the exit section. Okay. And obviously the remaining part of the code is the remainder section or RS. So when you try to analyze this particular solution, what I'll suggest is, instead of trying to find out how the statements are written, you try to find out whether this will meet your solutions or not. That means whether all the three requirements, mutual exclusion, progress and boundedness, are met by this entry section and the corresponding exit section. So this is the entry section of the code. And this is the exit section of the code. Okay. So I'm not going into analysis of this. You try to analyze this particular solution. So whatever solution to the critical section problem we have discussed till now, they are called software solutions, because you find that on these solutions we have written some algorithm so that the requirements of the critical section problem is met. Okay, so these are called software solutions. Now, in addition to these solutions, some machines provide some hardware instructions which can also be used for implementation of the critical section problem. When I say these are hardware instructions, that means it is a sort of function, but the function is executed like an instruction. Okay, so it just takes one machine cycle to execute the instruction, or we can say that the functions are atomic in nature. Okay. So if we employ such a technique, this is called hardware solution. So hardware solution can be used if the machines provide it. If the machines does not have such hardware instructions, hardware solution cannot be employed. Now typically some machines give hardware instructions like this. One of the hardware instruction or hardware function that has been implemented is what is called a test and set function. Okay. So it is something like this. We can declare this as a function test and set, and this works with an argument, a Boolean argument. Let us call the argument is target, which is of type Boolean, and this function itself returns a Boolean value. Okay. So the function test and set, it uses a Boolean argument and the function returns a Boolean value. Okay. So the function can be written like this: begin test and set is equal to target, and target is equal to true. Okay. So what does it mean? When you execute this function, the test and set itself gets a value which is equal to the value of the target. And after this, the target is assigned the value to. Okay. That means whatever value of the target with which this test and set function is called, the test and set function returns the same value. Okay. So if initially the target was equal to false and test and set has been called with target equal to false, since the value of the target is assigned to the function, so this function will return a value false. Okay. After that, the target is assigned value 2. That means all subsequent calls to the same function test and set will return a value 2. Okay. Until and unless the target itself is modified in between. Okay. So this is one hardware function which is supported by some machines. Some other machines support another hardware function which is called a swap. Swap is like swapping the contents of two registers, things like that. Okay. And that can also be written like this: procedure swap. Okay. And because it is the swapping of values of two registers or two variables, so naturally it has to work with two arguments. Let us say the arguments are a and b, and these arguments are of type Boolean. Okay. It has a local variable, say temp, which is also of type Boolean. The function works like this, the procedure works like this: begin this is simply swapping operation. So temp equal to a, after that a will get the value of b, and then b gets the value of temp. Okay. So what it does is it simply interchanges the values of a and b. Okay. So depending upon the initial setting of the target or initial values of these variables a and b, I can use either test and set or swap to provide solution to the critical section problem. Okay. Now simply let us see that how you can use this test and set to implement some mutual exclusion. Okay. So solution that is suggested is something like this. Still we have some common variables. The common variables are Okay. So as before, we have the entry section and the exit section. In the entry section, what process I does is it sets waiting I equal to true, indicating that process Pi is waiting to enter the critical section. Then it sets its local variable on local variable key is equal to true. So these two variables j and key, they are local to process I, whereas these two, the waiting, array waiting, and the variable log are the global variables or common variables. Okay. So after setting waiting I equal to true, process Pi sets its own local variable key also to true. Okay. Then it executes this while loop. In the while loop, what it does is it checks that while waiting I and key, then it executes this statement test and set on log. Okay. Initially, all the elements of this array waiting and the variable log, they are set to false. Okay. So you find that I can have a situation that a number of processes will wait in this while loop to see whether they can enter this critical section or not. Now, out of them, the first process, because if you see the nature of this function test and set, here what we have done is whatever is the initial value of target, in this case, this target is replaced by log. Okay, that is the argument which is passed to the function test and set. So whatever is the initial value of target, this test and set returns the same value, and after that target is assigned a value to. So all subsequent calls to test and set with the same target will return value 2. Okay. So here what happens is, since we have assumed that initially the value of log is false, and initially all the elements of waiting, array waiting, they are also false. Okay. So whenever ith process wants to enter the critical section, it sets waiting I equal to true, it sets key equal to true, then in this while loop, it executes key equal to test and set log. So if this ith process is the first process to execute this while statement or to execute this test and set statement, then only the ith process will find value of log equal to false. Since value of log equal to false, so key will assume a value false, and after that log will be set to a value true. Okay. So all other processes who executes this same statement test and set, they will find that value of log is equal to true. True. The first process will find it false. All other processes will find that to be true. So this while loop, where the condition is while waiting I and key, only for the first process to execute test and set will get value of key is equal to false after executing this statement once. So it has to be executed at least once. Okay. So after executing this statement once, the first process will find key equal to false. All other processes, because they get value of log equal to true, which has been set in test and set instruction itself, they will find value of key is equal to true. Key is a local variable. So for every process, you have a variable key. So except the first process, all other processes will find value of key is equal to true. So it is the only the first process for which value of key will be equal to false, and this while loop will be broken, and that will enter the critical section. Okay. No other process can enter the critical section as long as this process is in the critical section. Okay. So that is how you ensure mutual exclusion in the entry section itself. Okay. In exit section, what you are doing? You are setting a variable j is again a local variable, to I plus 1. Mind you that till now, it is the ith process which is active. All other processes are waiting in the while loop. Other processes who want to enter the critical section, they are waiting in the while loop. Okay. So only the ith process will execute this exit section. Other processes, since they are waiting in the while loop, they cannot enter critical section, and obviously entering the exit section does not arise at all. Okay. So in the exit section, what the ith process is doing, it is setting its local variable on local variable j to I plus 1 mod n. Now this modular arithmetic is used because we have n number of processes. Okay. So it sets j equal to I plus 1 mod n. Then it tries to see that whether jth process also wants to enter the critical section or not. So the process which will enter the critical section next, that has to be decided in the exit section of the ith process. Okay. So it sets j to I plus 1 mod n. I is its own identification, so it tries to find out whether the next process in the chain is willing to enter the critical section. Then, while j not equal to I and not waiting j, do j equal to j plus mod n. Now, why this statement? J has been set to the next process in the sequence, but it may so happen that jth process does not want to enter the critical section. Then you should decide who is the next process who will enter the critical section. So it checks that not waiting j is true, that means waiting j is false. So you find that if jth process is willing to enter the critical section, that would have set waiting j equal to true in its own entry section. So here, if it finds that waiting j is equal to false, that means jth process does not want to enter the critical section. So you check the next process in the sequence. So that is why you execute this statement that j equal to j plus 1 mod n. That is to come to the next process in the sequence. And how long this should continue? If there is no other process willing to enter the critical section except the ith process who has already entered the critical section, then I should not continue in this while loop indefinitely. So I have two conditions, that while j not equal to I. So if it so happens that no other process is willing to enter the critical section, so you have completed the entire chain and come back to a condition when j equal to I. So you should be able to break this while loop. Okay. So in this while loop, we have two conditions, that while j not equal to I and not waiting j, do j equal to j plus 1 mod n. Okay. After that, what we are doing is, now I have to set a condition so that either I can go back to the initial setting, or I will enable the other process in the sequence who wants to enter the critical section to enter the critical section. Okay. So that is what is done here. At the end of this while loop, if I find that j is equal to I, that means I have followed the entire chain but didn't find any other process who is willing to enter the critical section. That means I am back to the initial state. And what is my initial state? Initial state is lock is false, all the components of waiting are also equal to false. Okay. So in this initial state, if I want to go back to the initial state, what I have to do is I have to set lock to false. Okay. If I cannot go back to the initial state, that means there is some other process in the sequence waiting to enter the critical section. Then in the jth, in the exit section of the ith process, what is done is waiting j of that corresponding process is set to false. Okay. So when waiting j of the process is set to false, for the jth process in the entry section while loop, waiting j has been made false. That means this while loop will be broken for the jth process. So jth process will be able to enter the critical section. Okay. So that is how we have already ensured that in the entry section mutual exclusion is guaranteed. But we also have to check that whether the other conditions or other requirements are also satisfied or not. And among other requirements, we have the progress requirement. That is, the processes who want to enter the critical section, the decision of who will enter the critical section has to be taken among those processes only. So that is also taken care by this while loop. You find that if I find that weighting j is false for a process, I am not checking that process at all. I am just skipping to the next process. Okay. So progress requirement is also met. The third requirement, that is bounded waiting, whether it is met or not, that is also met by this solution, because you are checking all the processes in a circular manner, 0 to n minus 1, then coming back to 0 again. So you find that the and this decision is taken by the ith process itself. If I is equal to 5, then the fifth process checks whether the sixth process wants to enter the critical section. If the sixth process wants to enter the critical section, then weighting 6 will be made equal to false, which will enable sixth process to enter the critical section. Okay. Now, when sixth process comes out of the critical section, it will check whether the seventh process wants to enter the critical section or not the fifth process. It will check the next process in sequence whether that also wants to enter the critical section. Okay. So this way we'll find that every process will get a chance to enter the critical section, and before that process gets a chance to enter the critical section, at the most n minus 1 number of processes can enter the critical section, not more than that. Okay. So from the time of putting the request to actually getting access to the critical section, in between, at the most n minus 1 number of processes can enter the critical section. So that is also bounded. So find that this solution meets all the requirements, mutual exclusion, progress, and boundedness of critical section solution. Okay. And that here we have been able to implement using this test and set hardware instruction. Okay. Of course, the other things are required, because test and set will always guarantee mutual exclusion, but others are not guaranteed. So to guarantee that other requirements are also satisfied, we have to put these different data structures and all.